Okay, this is the third truss problem that I gave you in the practice. Okay, so we're going to go through and solve this one. So this one's a little bit more unusual just because of the torques. I want to make sure everybody knows how to do those. Okay, so joint A is penned, which means it has a vertical and a horizontal reactive force, potentially. And then joint C is rolling, which means that it's allowed to move in the horizontal direction, so there's not going to be any reactive force in the horizontal direction, but there is a vertical force. So now when we figure out what the first step is always to figure out the external forces if you can, using the conditions of static determinacy. The first one that we're going to use is that the sum of the moments equals 0. So remember, moment means torque. So we're going to pivot around this point, joint A. You can choose any pivot point you want. So we have a downward force at B, which is our external applied force. That's going to give it a clockwise torque, which I'm drawing in green here. And then there's going to be a counterclockwise torque, which must be this force at C. And so it must therefore be pushing up, because you can't have any torque around the pivot point, even though there is an upward force here. Because I chose this as my pivot, it can't torque around that, right? Because there's no arm length, it's 0. So there's 0 rotation around A, or 0 torque at A. So we're going to say that the sum of the clockwise torque and the counterclockwise torque must equal 0. And so we're just going to use the torque arm lengths and the forces pushing up or down. So if we draw this line straight out and make it an orthogonal line, so perpendicular to the applied force, then this is my torque arm all the way out to here. And so the pivot arm is orthogonal. And so when you figure out the clockwise torque here, the green, it's the force here, 60 kilonewtons, times 10 meters. And that's because this first distance here is 5 and the second distance here is 5. And so it's really just whatever the x component of this is, right? So it's not this entire length here, because it's the length of the arm that is perpendicular to the applied force, and so that's 5. So the entire torque arm for the 60 kilonewton force down is 10 meters times 60 kilonewtons. Plus, and then we have this one that's the shorter arm, right? This is 5 meters, and then this one's pushing up. So we're trying to solve what FC is, the reactive force that supports C. And you can probably already tell that it needs to be double because it's half the distance. But in case you can't, you can plug in the numbers, and that should give you 120. I wrote newtons there, but that should be kilonewtons. It should be the same unit here. Messed up there, sorry. I don't think I realized that. I don't think I ever erased it and fixed it. So 120 kilonewtons, it's double, and that's because the pivot arm is half as long. And so that's pushing up. Now we need to figure out the other reactive force here at A. So FA plus, in the y, sorry, just the y arrow, we'll worry about the x arrow in a second, FAY plus FC plus this 60 kilonewtons is going to equal 0. And so this downward arrow is actually negative 60 kilonewtons. This upward blue arrow is pointing up, so it's positive 120 kilonewtons. FAY is actually negative 60 kilonewtons, which means it must be pointing down. Now you can either think about that conceptually, that 2 downward 60s must equal 1 upward 120, or you can remember the signs, that if this is negative 60 and this is negative 60, this is positive 120. Whatever the case may be, you need to obtain the fact that this is 60 kilonewtons at A and that the arrow actually points down. So I'm erasing it and drawing a downward arrow, because that must be true for these vertical forces to all equal 0, right? Now I put a negative sign here, and I wrote up here, this is technically a negative 60. Now, just as I mentioned in the last video, the signs here for the external forces, we often do use positive to indicate either up or to the right, and the negative would indicate down or to the left. But when we ultimately figure out the internal forces in each member, instead of giving signs to indicate direction, we're going to say that it's under tension or compression, and that will sort of count as the direction. Now, this horizontal force, FAX, must be 0. So even though we thought there was a force there because it was pinned, because there are no other horizontal externally applied forces, because this is straight down, then this must equal 0. Okay? So you start with the assumption that there's a force there, but then when you realize that there's no other external applied forces, then we say that that's 0. Now here, I'm going to figure out the geometry of this triangle because I'm fairly confident that it's going to be important in a few minutes. And so if you're given, sometimes you're given angles, sometimes you're given dimensions, sometimes you're given both, but you generally need the angles within your structure so that you can do some trig on them later. So I'm going to go ahead and do that. I'm going to draw a line straight down here, and I know that this is 5, and I know that this is 5. And so this is an isosceles triangle, right? I know that both of those sides are the same length, which means that both of these angles must be the same. And because this is a 90-degree angle, I know that this is a 45-degree angle in both of these corners. So what does that tell me? So I can figure out the length of this side here, right? Because it's the square root of 50, which is 7.071. I just used Pythagorean theorem to do that. I can figure out this angle in blue because it is 180 minus 45, which is 135. This next thing here, this is the law of cosines. So I'm going to figure out, using the law of cosines, I know, so these A, B, and C are the length of these sides. And then capital C is the angle, 135. So if I want to find this distance here, I already know this distance, and I already know this distance. If I want to figure out this distance, then I can use the law of cosines, which is here. So you just plug in the numbers, right? A is this length here. Oh, did I do that wrong? Oh, I guess actually it doesn't matter as long as I get C right. Right, so C, the angle C is across from the length C. So actually it wouldn't matter if I swapped A and B here. A is usually the angle, the side across from angle A, but whatever. So you plug in A and B here and here, and then you plug in the angle 135, and then you figure out that C must be equal to 124.99. Oh, that's C squared, and so C is 11.18, so I'm going to label that. That would be a really long hypotenuse, right? 11.18 meters, and so now we can figure out this length as well. So if we're using this as this right triangle, then I can use that the sine is equal to the opposite over the hypotenuse. And I'm using this green triangle, right, because that's my right triangle. So that means 5, and the hypotenuse is 11.18, which means that the angle A is 26.565 degrees. And I can figure out B using also sine is opposite over hypotenuse. You could have also subtracted these two from 180, and that should still give you the same answer. So 63.4, that looks like a 3 degrees. So now I know all the angles, and I feel like those are going to be kind of important. Now this internal angle here, the actual angle in the structure is 18.4 degrees. So I'm going to include that because remember I was figuring out the angle of this right triangle. So the little angle in here is 18.14 degrees. So now I'm going to keep that geometry in mind as I solve some of these values. And so we're going to start with joint A with the method of joints. And we're going to remember that the forces are only along the members. There is a reactive support force that goes straight up. And then there's AB, which goes in the direction of AB. And then there's also AC, which goes in the direction of AC. So those are the three forces. And remember that B we can decompose into an X and a Y component. So the vertical support force is -60. The only other vertical force is supplied by the AB vector. So FABY, right? So the sum of the forces in the Y dimension are going to be equal to this vertical reactive force at the support A, which is FAY, which we already figured out is negative 60 kilonewtons. And then the y component of this blue vector is FABY. Those must sum to be 0, which means FABY must be 60 kilonewtons. Now we can use the sine of this angle, which we figured out in the last step, is equal to the vertical component here, opposite over hypotenuse. And so now we're going to solve for FAB. So that's the force in this internal member AB. So 60 kilonewtons divided by the sine of 26.6, and you get 134. Now when we figure out tension and compression, that's the next question. So the arrow is pointing away from the joint, which means that the internal forces in that member point out. So that is tension. Okay, so this pointing out is sort of stretching, pulling. That's a tension force. And we can also sort of try to think about it with our structure. Let's do that again. Let's do that for this structure. Let's look at each member and decide what we think is happening. So now if I take my structure and I pull down the way this weight is pulling down, and I all of a sudden remove this member, what's going to happen, I think, is this AC member and this CB member, they're just going to go splat on the ground, right? Splat. If I break that, and that implies that this member was holding it together through tension forces, right? Because it's pulling out. So I think it's going to splat to the floor just like that. So that means tension. Now if we do the other members, so if I erase all this and I remember the forces pulling down, and then I all of a sudden decide I want to remove this member BC, right? If I remove that member, then I think what's going to happen is it's going to collapse inward, right? Like a little Pac-Man eating, right? Do you guys even know what Pac-Man is? So that implies that that BC member is under compression. It's being squished down. Now AC, not sure I can even envision what AC is going to be. Yeah, I think I gave up on AC. Let's see, if I pull down, I don't know, I think it's under compression, but AC is hard for me to figure out, sort of thinking about it. I feel like I'm pulling down and it's being squished, I think, because it's pulling down and that's going to push this member down. So I think it's under compression, but I'm not 100% sure that that's true. So we're going to wait until the end until I can figure it out with the arrows. All right, so at joint A, we have these values. Now, if we're going to figure out AC at this point, we have our horizontal forces. The sum of the forces in the horizontal direction must equal 0, which means that FAC, that's purely X component, plus the X component of FAB, so FABX, the sum of those must equal 0. We can figure out FABX because we know what FAB is, and we also know what FABY is. And this is where I was going to try to remember to tell you the sign convention, that when it's up or to the right, it's positive. When it's down or to the left, it's negative. But that we usually remove the sign convention because if we indicate tension or compression, then we don't care about the sign anymore. So now we're going to calculate FABX from FAB. We're going to calculate FABX from FABY using the tangent. Right, opposite over adjacent is going to be equal to the tangent of 26.6, and so we can solve for FABX. And I think I plugged in 60 for FABY because we figured that out in the last step. So FABX is 120 kilonewtons, which means that that's going to equal the force of FAC because they are the only horizontal components. And so FAC must also be 120 kilonewtons. We're going to not worry about the sign because what we're going to say is that this is under compression. So I guess we were right, but I was wavering on whether this member was in tension or compression. But now we know because the arrows face the joints, that means those are reactive arrows, and that the internal forces face inward, and inward facing arrows means compression. So that's a compression member. Now last but not least, we're going to do the force in BC. So let's look at joint B. Joint B has a downward force. That's the external applied force, and there's also a force along these vectors that go along with the members. We know that because this member was under tension, that this arrow must point away. And so if this member points away, and those are both down, that means that this member BC must point up in order to balance the vertical forces. So I know that BC points toward joint B. And so now I'm decomposing the AB vector, FAB, into an FABX and an FABY. And so if this blue arrow is pointing up, it's also pointing to the right. And so I know that the right x component of that's FBC. I labeled it AC. It's FBCX. This x component must cancel out the x component from FAB. I think I'm going to fix that to BC in a second. So FABX plus FBCX equals 0. And then FABY, the vertical component here, and the vertical component of F, and I think this is where I realized I messed up and I changed that. We're going to add in this external force as well. So this is actually FBCY. So we have 3 vertical components, 3 vertical vectors that all sum to 0. FABY is negative 60. We calculated that earlier. This negative 60 kilonewtons, that's the applied force, the load. And then FACY is what we're trying to figure out, right? And it's not FACY, it's FBCY is this blue one I'm trying to figure out. I mislabeled it here. But I think in a second I'm going to realize that, yeah, see here I'm trying to change that to a BCY, and I think up here I changed it to a BCY. I don't remember if I ever changed it here. So FBCY is 120 kilonewtons. And now if we want to figure out what is FBC, right, that's here. This angle is 45 degrees. I feel like I saw it. Okay, so 120 kilonewtons, cosine of 45. Okay, so that's this angle here. Remember, this was a 45, 45, 90 triangle. FBCY, that's this component, and we're solving for FBC, which is here, right? So we want this vector, and then cosine is adjacent, which is FBCY, divided by the hypotenuse, which is the vector we're looking for. And we solve for FBC, and we get that it is 170 kilonewtons. And since the arrows point toward the joints, then the internal arrows point away from the joints, and that is compression, right? So this one is under compression. I think that matches what we said earlier anyway. So I put a little C here for compression.